Space is big. Not just big, it's colossal. We've stepped on our own moon a few times, and that's the farthest we've ever gone. It may have been a giant leap for mankind, but in the scope of the universe, we didn't even leave our front yard. So what would it take to travel through the void of space? A futuristic spaceship? A ridiculous amount of fuel? In this video, we'll try to understand, in terms of energy, how to reach the nearest star to us, Proxima Centauri. To make it more enticing, it might be worth mentioning Proxima Centauri b, an Earth-sized exoplanet in the habitable zone of Proxima Centauri's solar system. Its habitability for humankind is rather undetermined, but considering that it's the closest exoplanet to Earth, it might be a good goal to have in mind, in case this whole Earth thing doesn't work out. So, let's go to Proxima Centauri. How hard can it be to reach the nearest star to us? After all, we've sent hundreds of missions into space before, and some of them, like the Voyager spacecrafts, have even left the solar system completely. Well, to put it in perspective, Voyager 1, which is the fastest outward-bound spacecraft we've ever launched, has covered only 1/600th of a light year over the span of 30 years, and is moving at 0.005% of the speed of light. At this rate, a journey to Proxima Centauri would take 80,000 years. Since Proxima Centauri is 4.25 light-years away, the magic number is 10% of the speed of light. Traveling this fast would make the trek last 42 years, which is a length of time well within a human's lifespan. For this reason, any successful means of manned interstellar travel should be capable of reaching at least 10% of light speed, and slowing down at its destination. That last part's important. Even if you reach high speeds in a spaceship, you'll need to exert force in the opposite direction, lest your ship continue on through the cosmos forever. We'll have to factor this in constantly. One last thing before we begin, the Tsiolkovsky rocket equation. This displays a fundamental difficulty in rocket science. You need more fuel to increase velocity, but doing so also adds weight. And since we're focusing primarily on energy here, it's worth noting that to achieve a large velocity, energy is required according to the following equation. However, to make it even more difficult, this only factors in the energy required to make a ship reach a specific speed. In reality, as mentioned before, a spaceship will need an equivalent amount of energy to slow down at its destination. This doubles the energy required to k equals mv squared. So, how do we achieve interstellar travel? Here on Earth, we get our energy from a lot of different sources, not just the sun's rays or radioactive decay. So let's start by looking at a few things that won't work. Coal, too heavy, not enough power. Gasoline, too heavy, not enough power. Biofuel, too heavy, not enough power. Also, there's no corn in space. Geothermal, there's no geo in space. Hydropower, there's no hydro in space. Wind power, there's no winds. Well, we'll get to that later. Photovoltaics. This does use the sun's rays, and solar panels are often used in spacecrafts in the inner solar system, but it becomes much less practical once a spacecraft reaches the outer solar system. Since we want to leave the solar system entirely, we have a problem. For an interstellar spacecraft to get the same amount of current from solar panels in deep space as a 1 meter squared solar panel on Earth, its solar panels would have to be 2.5 times the area of Los Angeles. It's not efficient. As far as we can tell, none of these are the right fuel for long manned space excursions. Fortunately, we have other options. I've broken up our 12 main choices into 4 categories: present day, near future, mid-future, and far future. Present day options are options that have already been used for space travel. Near future options are technologies which have been extensively tested but not yet used in a mission. Mid-future options are likely to be possible in under 1 century. I was pretty conservative with this number, but in reality, a lot of these technologies could probably be deployed as soon as within a few decades with enough funding. The far future options might be possible, but certainly not for a century or more. It's pretty advanced stuff. Let's start with the present day options, the means of providing energy to space travel which have already been used extensively, and see how they would work on an interstellar journey. The first should be pretty obvious: traditional rocket fuel. This is a broad category that warrants an entire video of its own. Chemical fuel can be used in a liquid form, which is more easily controllable, or a solid form, which is cheaper and safer. Within those categories, there are lots of different types of fuel: kerosene and liquid oxygen, liquid hydrogen and liquid oxygen, hydrazine, liquid methane, and more. Chemical fuel has been used more than any other form of propulsion for space travel because it's so effective at getting a rocket off of Earth and into space. However, it has some drawbacks. Firstly, solid rocket fuel all goes off at once, like a firework, and it can't be controlled effectively. In most situations, liquid fuel is preferable. Yet, pretty much every kind of liquid fuel needs to be kept really cold, lest it boil off and evaporate, or worse, expand rapidly, possibly exploding and causing catastrophe. For our purposes, however, all chemical fuel has an even bigger drawback. It's just not fast enough. Apollo 10, the fastest manned vehicle ever, reached about 40,000 kilometers per hour using liquid oxygen and liquid hydrogen as fuel during their return journey. If a vessel was moving that fast toward Proxima Centauri, it would take 100,000 years to reach it. Don't get me wrong, traditional rocket fuel is great at getting things off of Earth, and will almost definitely be used in conjunction with other means of energy production for a long time. But if we're trying to reach other stars, chemical fuel simply can't get the job done alone. And while there are other types of chemical fuel, as mentioned previously, none seem to be suited much better for interstellar transport. Liquid methane, for instance, is being considered by SpaceX for possible Mars missions thanks to its energy density, inexpensive cost, and even its ability to be gathered in deep space or produced on planets. SpaceX CEO and lovable James Bond villain, Elon Musk, unveiled a plan in 2016 to do just that: build a propellant farm on Mars to produce methane fuel for return journeys. Yet, despite its apparent promise as the chemical rocket fuel of tomorrow, it's still too slow for interstellar travel. Fortunately, not every spacebound vessel relies solely on these fuels. Some of the most famous vessels to leave Earth have been powered by more long-term means, like radioactive decay. By using a radioisotope thermoelectric generator, or RTG, not to be confused with RTJ, radiation from decaying elements like plutonium can be converted into electricity, and a spacecraft can be powered for extended periods of time through this. For instance, take Voyager 1, which was launched in 1977. Its RTG will continue producing electricity until 2025. Likewise, the Curiosity rover is expected to remain powered by its RTG for at least another decade. However, though this radioactive decay provides these machines with energy for long periods of time, and with minimal human interaction, it doesn't provide a lot of energy at once, and it's typically used to power onboard systems rather than provide thrust. For these reasons, there aren't any seriously proposed interstellar spacecrafts which rely solely on an RTG for power, although, due to its simplicity, it's entirely possible that this technology is used in conjunction with other options in the future. So what about combining it with some present-day propulsion technology, like ion propulsion? It sounds like science fiction, but it's science fact. This method of propulsion creates thrust by accelerating ions with electricity. As such, it can be fueled with such elements as xenon gas, mercury, or iodine. It can also use electricity generated by an RTG. Some famous ion propulsion-powered spacecrafts include Deep Space One and Dawn. Although ion thrusters can't really operate on Earth and generate an extremely small amount of propulsion, their strength is in their constant thrust over time. A car propelled with equivalent thrust would take 2 days to reach highway speed. Yet, with its constant propulsion, ion thrusters have been hailed as the key to deep space exploration and a breakthrough for interstellar precursor missions. Of course, one problem with ion propulsion is that being powered by a fuel in the form of an inert gas, it has to actually hold all that fuel. A fascinating concept from the 1960s was the Buzzard ramjet, which would use a huge magnetic scoop to collect interstellar hydrogen so that not as much would be necessary initially, and it would never run out. Unfortunately, since its proposal, it's been discovered that interstellar space has a much lower density of hydrogen than previously thought, making this concept infeasible. Let's move on to the near future means of interstellar energy production. Plasma propulsion engines are like ion thruster engines, but kicked up a notch. Specifically, the Vasmer method seems to have a lot of promise, despite not yet being used on any missions. The concept is, radio waves ionize and heat a propellant, like argon gas, which is then accelerated with magnetic fields to generate thrust. This can provide pretty fast acceleration. Former NASA astronaut and founder of the Vasmer concept, Franklin Chang Diaz, famously claimed that it could get people to Mars in 39 days. Unfortunately, though Vasmer could be a quick way to traverse the solar system, it suffers from the same flaws ion thrusters and liquid fuel and solid fuel. Carrying large amounts of fuel will weigh down the spacecraft. As it stands now, a Vasmer-powered spacecraft can only reach 0.001% of light speed, a far cry from the magic 10% needed. This would take well over a millennium to reach Proxima Centauri. Admittedly, that's down from the tens of millennia that traditional rocket fuel would take, but it's still not exactly ideal. There is still a pretty obvious way to fuel a spacecraft that we haven't discussed yet. Nuclear fission supplies over 10% of the world's electricity via nuclear plants. Surely it can work in interstellar space travel too, right? Fission involves getting power from radioactive materials, much like an RTG. However, unlike an RTG, fission doesn't just wait for elements to decay. It forcibly splits them, launching some of its neutrons into other atoms, causing a chain reaction of split atoms, all of which release more neutrons and tremendous amounts of energy. This is typically done with uranium. This is the source of energy needed in nuclear thermal rockets. Perhaps surprisingly, no nuclear thermal spacecraft has ever been used in a mission. For nearly 2 decades, there was a nuclear thermal rocket engine development program called NERVA, but it ended in 1972 due to a loss of political support despite successful research and testing for years. Its goal to send a manned mission to Mars by 1978 was seen as too much of a financial commitment for the United States, and at the time, many politicians wanted to end the space race to cut spending. So, can a nuclear fission-powered spacecraft make it to Proxima Centauri in a human lifetime? How close can it get to that magic number, at 10%? A fission-powered rocket like NERVA, due to the weight of the reactor and fuel, probably tops out at 5% of the speed of light. This isn't bad. That would make an interstellar voyage last about 90 years. Plus, it uses technology that's been around for decades. But when you factor in deacceleration, this doubles the amount of fuel needed, and most likely doubles the amount of time for the journey to around 180 years. Still, we're getting closer. If we're already using nuclear power, why not just take it to an extreme? What would happen if we built a spaceship that just drops nukes behind itself? As it turns out, this crazy-sounding idea is called nuclear pulse propulsion, and it's been around since the 1950s. The most famous concept for such a spacecraft is Project Orion, which was first designed in 1958 by Freeman Dyson. You might recognize that name. Dyson considered 2 different designs for the project: the larger but slower energy-limited build, and the smaller but faster momentum-limited build. We'll focus on the second one, since it's a lot faster. By essentially dropping and detonating nuclear warheads behind it, this spacecraft can reach 10% of the speed of light after 1 month of acceleration. That's the magic number. But it still needs to slow down, so the journey is looking like it'll take nearly a century. Still, this is 10% of light speed, which can be achieved by dropping bombs that we already have. As astrophysicist Carl Sagan once noted, this would also be a great use of nuclear weaponry that doesn't involve blowing each other up.
You'd be destroying a lot of nuclear weapons in the process.
If this all sounds a bit reckless to you, you're kind of right. The original design of Project Orion did involve using nukes to launch from the surface of the Earth, which is obviously a pretty bad idea.
You would not want to launch too near the Earth.
Dyson later formulated an idea for launching Project Orion from low Earth orbit, which would be much safer but could still disrupt satellites, computers, and other technologies with an EMP. It could also potentially cause environmental damage, and the entire project really violates the partial test ban treaty of 1963. That being said, this is the fastest means of interstellar travel that we have right now. Maybe it'll come in handy in some apocalypse scenario, or maybe it can be used in conjunction with some other fuel source that gets it far away from Earth before exploding any nuclear weapons. Or maybe it's a reckless idea that will never ever be used. Only time will tell. There is one more kind of nuclear power worth discussing, and although I've classified it as mid-future technology, it may have more promise than anything yet discussed. Nuclear fusion. This is the energy that powers our sun and all the other stars too. It works in the opposite way of fission. While fission splits atoms into smaller ones, fusion combines atoms into bigger ones. This produces a ridiculous amount of energy. Fusion power has been subject to study and experimentation for decades, and some methods of nuclear fusion, like inertial confinement using lasers and magnetic confinement using magnets, have been pretty successful. Still, fusion has a long way to go before it's cost and energy efficient. But what could a fusion-powered spacecraft do if we can harness the power of stars? In the 1970s, Project Daedalus, led by engineer Alan Bond, sought to answer exactly that. Now, Project Daedalus was unmanned, which is an issue since we're specifically trying to understand the time a manned interstellar trek would take. But since Project Daedalus is the most famous concept for a fusion-powered interstellar spacecraft, it's very much worth discussing. This project sought to reach Barnard's star, which is farther away than Proxima Centauri, and it planned to reach it in under 50 years. By its design, it should be capable of reaching up to 12% of light speed. This is perfect. There are only 2 apparent issues with a fusion-powered spacecraft. First, as mentioned before, fusion power is not yet viable with modern technology. Second, this would require a lot of hydrogen-2 and hydrogen-3, also known as deuterium and tritium. Still, for 12% of the speed of light, fusion-powered space travel is probably the most immediately promising technology in this whole video. Now that we're firmly in the realm of mid-future technologies, let's talk about a really fun concept that doesn't need any fuel at all. Sails. Now, a solar sail looks a bit like a traditional sail you might find on a non-spaceship, but it's not quite the same. A solar sail is not propelled by wind because, as we mentioned before, there's no wind in space. Okay, we'll get to that later. A solar sail is pushed instead by photons. Basically, starlight propels it. Although there isn't much starlight at all in deep space, if a solar sail-powered spacecraft can accelerate enough before entering deep space, it'll keep going until something stops it. One proposed way to speed the whole thing up is to shine a really powerful laser at it. This is called beam sailing, and it could potentially bring a spacecraft up to 10% of light speed. Of course, this would require a very large laser pointer powered by nuclear fusion or something. But the point still stands that with enough money and resources, beam sailing could be viable. Not to mention, when the spacecraft gets nearer to another star, like Proxima Centauri, the light there will help to partially slow it down. The speed is mostly determined by the weight of the spacecraft, the size of the sail, and the strength of the beam.
People over just about a century ago realized if you had a spacecraft in space of low enough mass and it was big enough, it would get a push. And so my old professor, Carl Sagan, was a big advocate of this.
Each of these factors represents an engineering challenge. Of course, solar sails are not to be confused with electric sails. These don't look much like sails at all. They're more like space spiders. That's because they consist of dozens of positively charged tethers which gain their momentum from deflected solar wind protons. That's right, there isn't traditional wind in space, like the kind that can turn a windmill, but there is solar wind, a continuous stream of plasma that flows outward from stars. There are a few problems with using electric sails for interstellar travel, though. They can't operate that close to planets, they can't effectively travel against solar winds, and most unfortunately of all, they can only reach about 0.0001% the speed of light, with a light payload. So why are we even discussing them? Well, although electric sails are mostly designed for interplanetary travel, it's entirely possible that an electric sail serves as a braking system for an interstellar spacecraft. This could reduce the amount of fuel needed for slowing down. It's also worth mentioning that there's a third kind of sail, a magnetic sail, which is propelled not by solar winds, but by magnetic fields. Functionally, it's not so different from electric sails in that it probably won't propel an interstellar spaceship alone, but it also might make a great braking system. With that, we conclude the portion of this video discussing technologies that can reasonably be acquired within a century. It's time now to move on to far future technologies, the means of energy production that could, in theory, get humans to Proxima Centauri in a very, very, very short amount of time. To begin, picture this: a spacecraft powered by fuel, but it's not traditional rocket fuel. Rather, it's highly volatile, incredibly energetic, and the most powerful fuel in the universe. We're talking about an antimatter drive. To be clear, this isn't fantasy. Antimatter exists, and it's been proven time and time again that when an antimatter particle collides with matter, they annihilate each other, converting their entire rest mass into energy.
So if I have antimatter, if I touch it with ordinary matter, I would have complete annihilation, meaning that the efficiency of the bomb would be about 100 times greater than the efficiency of a hydrogen bomb.
In terms of energy density, antimatter fuel is 10 orders of magnitude greater than chemical fuel. That's 10 billion times more joules per kilogram. If you had antimatter that weighed as much as 2 quarters, that would be enough fuel to get to Mars in less than a month. With an effective antimatter rocket, a spacecraft could easily reach 10% of light speed. In fact, it could reach upwards of 50%. That would make a trip to Proxima Centauri take only about 9 years. There's one glaring issue with antimatter fuel, though. Containing antimatter is incredibly difficult, and with current technologies, we can only hold a few antimatter particles at any given time. This is because a container made of any kind of matter will react with the antimatter and destroy it. In 2011, however, scientists at CERN used a magnetic trap to hold antihydrogen, an antiproton orbited by a positron, for a full 17 minutes. This is obviously not even close to the amount necessary for antimatter rockets, but it's the first step toward the most efficient fuel in the universe. Believe it or not, antimatter power isn't even the most science fiction-like technology on this list. That's because this next source of energy literally appeared in a science fiction novel called Imperial Earth, decades before it was ever seriously considered as an actual means of interstellar travel. Enter the black hole starship. It might sound evil, but it's also known as a Schwarzschild Kugelblitz, which actually also sounds a little bit sinister. Still, this could be an incredible technology. Picture a microscopic black hole weighing more than 2 Empire State Buildings. Its peak power output is estimated to be 129 petawatts, which is a lot. Using a microscopic black hole for power would solve our energy production needs and take us to faraway stars. The science behind this involves capturing energy from Hawking radiation, a type of radiation expelled by black holes. By harnessing this power, even a very large and heavy vessel could travel through the cosmos at more than 10% of the speed of light, with reliable acceleration and deceleration. The issue with a black hole-powered ship is that a black hole has to actually be created first, which would take an immense amount of energy and resources, not to mention complications with converting the Hawking radiation efficiently into propulsion, and whatever obstacles come along with containing a microscopic black hole. Simply put, although it seems entirely possible mathematically, this technology is really far off. As great as taming black holes sounds, it's still not the fastest theoretical way to reach Proxima Centauri, which is the fundamental question we want to answer. As far as that goes, we saved best for last. The fastest we can feasibly go with a near or mid-future technology is probably around 12% of the speed of light, if everything works perfectly. With advanced far-future technologies like antimatter rockets or black hole starships, we could probably get upwards of 50% of light speed, which would make the trip to Proxima Centauri at 9 years or less. But what if we could get there even quicker? What if we could travel at 70% of light speed? Or 90%? What about 100% of light speed, the speed limit of the universe? Well, the Alcubierre drive can go even faster. By contracting the space in front of it and expanding the space behind it, basically riding a wave of space-time, the Alcubierre drive can travel faster than light without breaking any laws of physics. Think of it this way: if you have a sailboat on the ocean, you can make it faster with a bigger, better sail, or a more hydrodynamic design, or more winds, but fundamentally, that sailboat can only go so fast. However, if the waves are pushing the boat along, it can go even faster than the top speed of the boat otherwise. Better yet, if we could artificially manipulate the waves, like with a propeller, then we can make a really fast boat with much better mobility. This is analogous to the Alcubierre drive, which is a sort of interstellar propeller, disrupting the fabric of space-time to seemingly travel faster than light. Although this all works in a theoretical sense, actually building an Alcubierre drive is a much greater challenge. This is probably the most distant technology of everything listed, and although it has been conceived of and discussed at length, it will almost certainly take a few dozen decades before any significant progress is made on it, if any at all. There it is. 12 energy options that can be used to power a manned interstellar spacecraft, each with varying degrees of efficiency, complexity, and viability. It's worth noting that this isn't nearly a comprehensive list. There are some sources of energy, like solar panels, which play a role in interplanetary spacefaring, but didn't seem worth mentioning in an interstellar context. Still other technologies, like EM drives or cold fusion, are based on unfounded or underdeveloped science. Most importantly, there are future technologies out there waiting to be discovered. As it turns out, rocket science isn't easy. Combined with the many obstacles that space provides, achieving interstellar travel would certainly be the greatest feat humanity ever accomplished. Like many challenges, it can seem, at times, insurmountable. That being said, it's possible. We have the means to achieve interstellar travel, theoretically even within a lifetime. Past are the days where stories and ancient mythologies were the only ways to reach the stars. The fact that we can discuss it with real data and tactile blueprints means that the moon isn't going to be humanity's last stop. Space may be colossal, but we've already taken the first giant leap. Thanks for watching. If you'd like to see more videos like this, let me know and share it. I'd be happy to cover lots of different topics in the future.